Good afternoon. No, actually, this one goes to the video that's going on to YouTube. So it doesn't make me louder, it just puts me on the video. So we are going to have to be slightly quiet so that we can hear Kurt's talk. I do want to thank everybody for coming today. The psychology lecture series is something that we put on once per month during the regular semester in order to give students the opportunity to learn something different outside of the classroom environment. Dr. Lucas, the microphone is not to make me louder. It only goes to the video. So, once per month we offer a lecture series to allow our students to learn something outside of the classroom, which also gives our faculty members the opportunity to talk about something that they're excited about to our students. So today I'd like to welcome Kurt. He's going to be talking about the amygdala, right? Is that how you pronounce it? Okay. Questions at the end or questions during? Okay, all right. So if you have questions, please let him know. Otherwise, at the end of the talk, I'm sure he'd love to answer your questions. I appreciate you coming again, and please make sure that you've signed in on one of the 3 sign-in sheets back there. And also, if you're interested, on November 5th, which is a Tuesday, the psychology department is offering Psychology Day over at the CCC from 9:30 until 12:30. And then we also have a speaker from 12:30 until 2 o'clock who will be talking about psychology in the courtroom. All right? Again, thank you for coming.
All right. So I'm supposed to click this.
You're on, by the way.
All right.
I made
Oh, thank you.
Oh my God.
Oh, shush. That's what you're here.
Yes, I dress them in the morning too.
No. It's catching on my pants. And there we go. Good, good, good. What was that? All right. Welcome, everybody. Quite impressed by the turnout. Only expected about 3 or 4 people, actually, and most of those would be instructors, I was hoping, but lots to cover. I've got a lot of hopefully semi-interesting stuff to show you that you can find of use at some point. Why the amygdala, right? Why did I pick that? And why almonds? Right? So when it was originally described way back in the early 1800s, the amygdala was described as almond-shaped. So sometimes you feel like a nut, right? Oh, come on, thing. There we go. All right, and I know I'm dating myself. I do it all the time in classrooms, but some of y'all may recognize that song way back in the 70s, right? And anybody else, you guys? Yeah, okay, well then, I don't feel so horrible. All right, so that's the whole idea behind the title to the talk. I just want to warn you that there are a couple graphic images of people that didn't survive their life too well, and so I just want you to be aware that that may pop up. So if you're subject to heart attacks, easily panicked, you need to go ahead and sign out, go on back. All right, so as little about myself as I can possibly tell you, I'll tell you right now that I'm extremely nervous. In case you can't tell, I have a tremendous amount of anxiety, and this is part of the reason why I'm really interested in the amygdala, is to try and figure out, well, what is it about me that makes me so prone to anxiety? And I've experienced it all my life. So if you're in that position where every single talk you get, you're just absolutely terrified. I mean, I had it in high school, in college, and throughout life, I've always been pretty darn terrified speaking in front of people. And then you might ask, and it would be a reasonable question, what the heck are you doing teaching? Right? So, and that's, but that's for another whole presentation in 10 years when I do this again, right? So, but how did I get over it? How did I survive this incredible anxiety to at least to the point that I can get up in front of you? Well, drugs help. That's a good one. And so they're certainly important. The second thing was graduate school. And graduate school taught me to really get pissed off when people are yelling at me during a presentation. So what happened was my first major presentation in graduate school was to a bunch of people, a bunch of scientists, and it had to do with circadian rhythms. And so it was a fairly technical talk. And this one guy latched into me, and he just ripped me a new one in that talk. I was very nervous giving it, and he just ripped me a new one. Then when I got out, my mentor ripped me a new one too. And so it was just like there's no win. I mean, I was absolutely ready to quit the program, but it was either do that, quit the program, or get angry about it, make sure that I could give the presentation in a somewhat reasonable manner and survive that way. Come on, back over here. And then, sorry. And so from that moment on, I was at least able to do presentations. Now, I will caveat that with in graduate school for my first defense, in graduate school you have to go, you present your, you do your own research, you go through and you start writing your paper, start doing, summarizing your research, and then you give that to your committee. And on my first committee meeting, I had my only moving accident I've ever had in my life. I was thinking about it and just driving along and just totally blew it. So anxiety is a funny thing. All right, so standing up here giving a speech can be somewhat intimidating, and the absolute best show ever given, ever presented is Seinfeld, right? Everybody agrees with that, right? Seinfeld's like #1 of all time. So in this particular episode, George is supposed to give a speech on risk management, right? And he's been mentoring this person who's written the speech for him, or so he thinks. At the same time, Jerry is mentoring a comic and has written a little routine for that comic. And of course, they get switched. And so here's George on Ovaltine.
Our next speaker is George.
Very cool. All right. So for whatever reason, my computer, it works fine, but when you get to Vista, of course, as you might know, the computers don't quite function quite as well. So that's the whole idea. And so what are the top fears? And you can go on the internet and you can find books that have, top 10 fears, and they're all completely different. But this one fit my needs. So this is the one that we used. And look at that, #1 fear, speaking before a group, right? And I've heard this most of my life, that was the #1 fear. And look at death down here, #7. Holy crap. My favorite, or my personal #1 fear, besides speaking before a group, so I guess my #2 fear is being buried alive. But that, I don't know that. Anybody else have that? No? Buried alive? Ouch. All right. Okay, so sorry, that was one of those images. So, of course, you all recognize her from The Exorcist. And this is why we're here, to figure out why do we fear things, why do we experience anxiety, phobias, and we may not solve all of it here in the next 45 minutes or so, but we'll try to get to some of it. And of course it has to do with the amygdala. And I'm experiencing a lot of the features of activation of the amygdala right now. So the amygdala's major role is linking alarms, right, with your body's fear. And that's the whole idea here. And the way it does that, unfortunately, is it has direct actions and links to the autonomic nervous system. And it's like a next door neighbor. It goes over, knocks on the door, says, hey, so go send that signal out, get that heartbeat racing, get that blood pressure up, get that, that mouth drying, on that note. Right? Get the mouth drying. What else can you think of? What else happens, right? That deer in the headlights look that you get when you're really scared. All these are obvious effects of stimulation of this particular pathway. Other things that you may not know or think about with the amygdala is it is going to take random stimuli and basically associate them with fairly reinforcing events. And we'll talk about that. There's a classic experiment with rats where we look at that particular issue. Looking at people's faces is a huge part of the real estate in your brain. There's a tremendous amount of detail that is discerned by the brain just from the human face. And humans are, of course, humans versus gorillas. Humans are just have I can't emphasize how important it is. And one of the roles of the amygdala is to look at these aggressive features, at fearful features, and be able to discern them and be able to react accordingly and emotionally support or do whatever you can. But of course, we're going to talk about people that can't do this particular activity. And the first experiment that we'll talk about is that neural activity in the amygdala brain of people with healthy brains increases significantly when they're viewing facial expressions of fear. So this is our first hint that the amygdala has some type of fear component associated with it. All right. If I'm going too fast, you need me to stop flipping slides or things too quick, just let me know. All right. On that note, I'll go to the next one. Okay, so let's look at the overview. Also, continue that. It establishes reward learning. Certainly very important. Again, something we can easily look at through certain experimental paradigms. One thing that surprised me in my research for getting ready for this presentation, it's this us versus them dichotomy. Where do we exist? You see that more than anything right now? Government, right? Us, the Republicans, versus them, the Democrats, and if they do anything, then doggone it, how are we going to react to that? And it's this very sharp separation. And indeed, anything that is them is responded to very strongly, and the amygdala has that charter. That's its job, is to respond to these them things and go, hey, that's not right, that's not for me, that's over there, that's not fair. We need to take care of that. Aids in social interaction, as you might guess, with this facial interaction that we have, a lot of social interaction. We all like to be popular, right? We all want to do that. We want to do things that make us more popular. When you get to my age, you give up on that, but you still would like to. In the back of your mind, you say, oh, I don't care what they think. But then in the back of your mind, you still do things that make people want to like you, right? So it's certainly very important in that aspect as well. And your morals. Damn your morals, right? God, they always get in the way, don't they? Stinking things. And then it helps weigh risk against gains. And what we're going to see, at least partially, is that what happens when the amygdala gets damaged is that these big risks that you're taking don't give you very substantial gains. And so people that have this issue, especially chronic gamblers, right, that are betting the house and all they're going to get is, a door to add to the house, that's the problem there, and they've got some kind of issue with the amygdala. Okay, so that's the overview of the function. Why should we care at all about the amygdala? Right, it's a hard word to spell. It's a little part of the brain. Maybe it doesn't even really matter. We could, remove it and wouldn't even miss it. Well, in people that are experiencing seizures, quite often they'll have an aura that occurs just before the seizure development. And in people that have these seizures that are near the amygdala or part of the amygdala, intense anger will be felt. Now, I don't want to imply that the amygdala has everything to do with anger, because anger is an incredibly complex outcome and involves many other parts of the brain than just the amygdala. If you show somebody that's sitting and trapped in a functional MRI machine taking pictures of oxygen consumption in their brain as they're doing certain activities, if you show somebody an image that's intended to make them either get very angry or fearful, then the region of the amygdala will show increased oxygen consumption. Increased oxygen consumption is allayed then with increased activity. That's the whole idea behind functional MRIs. If that's not true, they're all garbage. So in this case, hopefully they aren't. A thing that we'll keep hitting on during here is a realistic aspect. Something that's very prominent in today is amygdala in PTSD, post-traumatic stress disorder, right? So we'll be discussing its role there, and it's been shown that in individuals who suffer from this, the amygdala gets larger. Therefore, it tends to overreact a little more easily than you would expect. But more on that later. We can have people that experience lesions in the amygdala. How does it affect their lives? What are the natures of the lesions? And with some lesions that occur, they can't detect fear in faces. And that's very important. When you see somebody else that's fearful, that's a warning to you, right? That's how you can react to the environment. And so, very critical. And what they tend to do, instead of focusing on the eyes and the area of the mouth, they focus on the nose and the chin. That doesn't tell you much, right, about what's going on. If you think about it, eyes are everything, right? The way the eyes react, because all of us react maybe completely subconsciously to fear and anger and other anxiety-provoking stimuli with movements around the muscles of our eyes. If some people that have amygdaloid lesions are absolutely trustful. We'll talk about a genetic disorder that results in that. And so what I'm trying to get through to you, the main point here is the amygdala and stress go hand in hand, right? And how we deal with stress is absolutely dependent on the role your amygdala plays. And once again, point out the amygdala has a direct connection straight into the hypothalamus to get those stress hormones released. What other reasons are there? Charles Whitman. Anybody know who Charles Whitman was? All right, well, fine. Yes, I heard a couple yeses. So my brother was actually attending UT when Charles Whitman climbed the tower a long time ago. My brother's much older than I am, though. And in fact, this is his birthday today, so I think he's 65 today. So he's much, much older. And 40 years older. And so... at UT, we actually call it Whitman Tower. I mean, that's maybe a bad thing. I don't know if they still do that, but when I went to school there, they certainly did. So Whitman, it turned out, had a tumor that pressed on the amygdala. Now, the confound here is that the tumor also pressed other regions and other sections of the brain, but nonetheless, this occurred. Can we pop off that second light, the middle one? Thank you.
The first major sniper incident occurred in 1966 on this peaceful campus at Texas University. The sniper was a student who fired from this campus tower overlooking the whole city of Austin. Charles Whitman, 25, an ex-Marine sharpshooter. Like most snipers, he was a white middle-class honor student who had never committed a crime. One morning, he went to the top in this elevator.
Anybody else notice it didn't go on 25, right? What the heck?
All these guns. Whitman barricaded this door and used a dolly to pull all his supplies up these stairs, then hauled them out onto the deck and began methodically shooting people at random. The first victims are students walking across the campus, talking to friends, and going to class. Then Whitman aims at the city and kills random shoppers, and even a man in a barber chair.
This is a warning to the citizens of Austin. Stay away from the university area. Traffic is now converging on this area. A boy riding a bicycle has been shot and seriously wounded. There has been a report of a policeman in this area.
Try to rescue wounded friends.
There's another shot, and another shot. There are three
But some are already dead. By afternoon, 16 people are dead, and more than 30 seriously wounded. 3 police officers finally reach the tower.
The sniper was in this position. As he was distracted by the officers coming from the rear here, he turned in this manner. The officers fired around him here in this area with 6 rounds. The second blast was a round from the shotgun, which hit him here. This is where the sniper fell, here in this area here.
So some of those graphic images.
Police discovered that the previous night, Whitman went to this apartment building and stabbed his mother to death. Then he went home and typed, "I just killed my mother. If there's a heaven, she's going there. If not, she's out of her pain." Then he went in the bedroom and killed his wife asleep in their bed. But he didn't join her until he had shot 50 strangers. Within 5 years, snipers had become a fixture of American life. Usually they were hard-working, wholesome youths, frequently in the top 2% of their class, often still in high school.
So I remember Whitman talking about this strange feeling he had. It had been developing over several months, and how it was disturbing to him. He just didn't feel normal, he said, anymore. It wasn't, he couldn't go out and enjoy things like he used to. So big case, very interesting outcome, especially since it happened over at UT. There's a very famous terrorist organization out of Germany called the Red Army Faction, used to be known as the Baden-Meinhof Gang. The female leader, turns out, had a amygdaloid tumor. Certainly looks pleasant enough, but she was a out-and-out killer. And so let's look at a lighter side now. Rather than murder and so forth and mayhem, let's look at the amygdala in art. And so we have a first grader here who is writing the amygdala. And what she's doing, she's helping out someone who's teaching adults about parts of the brain. And so she's mostly correct. I mean, good enough for a first grader, I think, right? It's pretty awesome. It does have a lot of inhibitory functions and so forth, but some of the things she got are actually more to do with your cortical function, not so much the amygdala, but still like it. I don't know. This is about the only thing I could find that's funny in the least. I mean, I appreciate you laughing. I know you're being nice, but anyway, that's about it there. Turns out there's this DJ Coase right here wrote a song called Amygdala. It's amazing what you find when you go through. So let's hear some. And it goes on like this for about 4 minutes. It's the same. I would play you the whole song, but just repeat this for 4 minutes. And then in the bottom corner is a band named Amygdala. Right? All right, and that's pretty much the same for the next 4 minutes. So it turns out there's actually 3 bands, but they all sound exactly alike. So here's Amygdala, the anti-hero, right? He goes into rage and so forth. Amygdala, right? Right? So there's comic book heroes even about this stuff. And then, I don't want things to seem so negative with the amygdala. There are some positive emotions, even though this is completely wrong. But nonetheless, you find it on the internet. Hey, it must be true. And the feelings of love, right? But the heart gets all the credit, whatever. So doing it in honor of Dr. Don. I had all negative stuff, and then, I figured I should add a couple happinesses slide there.
In honor of me being misunderstood.
Oh, misunderstood. All right, so now to more serious stuff here. The light stuff's over. Let's get real. All right, where is this sucker? Well, hopefully you guys have covered the lobes of the brain. We have the 4 lobes and the temporal lobes, where we're going to be focusing on the amygdala in this real human brain found right in this region. And we see it right here in this more 3-dimensional approach, these little blue dots. And then you can see it here. And it's got a very intimate association with the hippocampus. More on that later. Just want to point that out. Okay, it's bilateral, as you noticed. And if you want to know where it is, stick a spike through your eye, one through your ear, and basically where they come together, that's where your amygdala is. Okay, so let's look at a film that shows it, I think, a little more 3-dimensionally, a little more all this beautiful music kind of lulls you to
The
sleep.
major aspect, the temporal lobe, contains a network complex of gray subcortical matter, amygdala. Note the inferior horn of the lateral ventricle. Here is a corresponding section of the real brain preparation. The cortex that covers the amygdala is called the uncus. The yellow structure in this T2-weighted MRI is a 3D reconstruction of the amygdala.
So you can see those eyeballs right there. So it's about that level, right? Does that look like an almond to you guys?
And then,
Not really. Somebody's imagination.
note its medial temporal position.
All right. Good to go there. Okay, so what are the major nuclei of the amygdala? And like Ms. Guerrero and myself, we really love neuroanatomy. I mean, if I could spend my life just tracing pathways and axons and so forth, I would do it. Because this is really where my heart lies, is tracing and looking at neuroanatomy. You guys might think, wow, what a loser. But anyway, what? So it turns out there's about 13 distinct nuclei that can be found here. This poor image, unfortunately, shows you most of them, but just gives you the complexity of the amygdala. We're not going to go through all 13 as much as I'd like to. We're not going to do it. We're going to kind of clump them together, and the so-called basolateral nuclei. And what you have to understand is every single sensory input that goes into a region of the brain called the thalamus also sends inputs to the amygdala. So all sensory inputs except one, let me show you, visual, auditory, somatosensory, which is basically touch. What am I missing? So sight, smell. Because smell does not get handled by the thalamus, at least not directly. We'll discuss smell, though, in a second. So every bit of visual information, every bit of hearing, every bit of touch is going to end up in the amygdala. And it may end up sooner than you wish it would. All right, so it turns out there are also inputs from the thalamus. I'll have a picture of where that's at here in a sec. The prefrontal cortex, what's that good for, right? Not much. No, it's actually you guys sitting here with your personalities, your judgments, who you are really, how you present yourself to the world, your affect, is handled through this ultimate of all integrative areas in the brain that pull together massive amounts of information and make an output, where you smile, you present yourself in a pleasant way, or you frown and you yell, right? It can do that as well. So the PFC is an executive controller. It will still, no matter what the amygdala may want to do, the PFC will still be in command. All right? And there are many other integrative areas in the brain that are also sending inputs to the basolateral nuclei. Let's look at the visual pathway from the thalamus to the amygdala. And this is a nucleus in the thalamus called the lateral geniculate nucleus. Not really important, but the thalamus is made up of many small clumps of neuron cell bodies, and each one is like a mini processor, right? And this mini processor, known as the lateral geniculate nucleus, is handling visual inputs. Okay? So the visual inputs go to there, they synapse there, and then most of the time, all of them will go back to the occipital lobe, all the visual information. But there's a little pathway that goes to the amygdala. All right? And unfortunately, it's only about a 10 to 20 millisecond difference in going to, in this pathway, the thalamus to the amygdala versus the thalamus back to the occipital lobe, then back to the amygdala. But that 20 milliseconds is enough to get you into enormous amounts of trouble. So just to point out, here we have the inputs. We've got the inputs going into the thalamus. These are all your sensory inputs. For this particular example, let's say it's the visual inputs. So most of it is going to go back to the occipital lobe, processed in the cortical areas here, and then sent forward to the amygdala. But there is a shortcut here. And that's the one that leads you into trouble, to overreacting too swiftly, to yelling at somebody right off the bat rather than, you know, why did I do that? Why did I just scream at the kids for no reason, or at my spouse, right? right? Do that all the time, right? And as it turns out, what's remarkable here is in PTSD, this pathway is actually bigger, better, conducts things much quicker. It's absolutely now a much more important pathway than in normal circumstances. The second major nucleus is the cortical nucleus. This one has roles. We're not going to go into this one too much more in depth, but it has roles in parenting skills, right? And in how you should treat your children, how you should interact with them. Was it successful? Good. That gives you positive feedback. Your amygdala responding kind. Did it suck? Well, okay, I guess I shouldn't do that again. So those kinds of things. Social interaction. Am I popular? How do I react to these people? I've got all you guys in here. Do I consider you enemies? Which pretty much is what's going through my head right now. Or do I consider you guys all friends? And this is going to be a friendly talk. We'll all get along and everything's great, right? And of course, associated with those then is establishing stress and anxiety levels. This one is located near the olfactory centers in the brain. This is where the olfaction part of alert and alarm comes in to the amygdala. So we have visual, right, sensory in terms of touch, and then auditory coming in through the basolateral nuclei, and then the cortical takes in that olfactory information. Finally, the big kahuna here is the output of the amygdala, right? Where are we sending all these outputs? What is it actually, who cares about it, right? Well, a lot of areas in the brain care about what the amygdala is doing. And connect to many other areas, those especially associated with emotional responses, the hypothalamus, the brainstem. And I'll show you some of these things. The VTA is called the ventral tegmental area. It is the source of dopamine in the brain. The locus ceruleus is the source of norepinephrine in the brain. What I didn't include here is the dorsal raphe that it also goes to. It's the source of serotonin in the brain. So hopefully you get an appreciation for how powerful now this thing is getting. I mean, it is controlling release of these absolutely powerful and essential neurotransmitters. It's going to have links to the hippocampus, right? Why is it when we have a fear, it begins ramping up more into anxiety and perhaps even eventually into panic attacks? It's because of that damn pathway between the amygdala and the hippocampus being so efficient at storing that memory away of being fearful. And of course, this is where we get our main output for why we're scared of things. It modulates our attention. If you remember nothing else today, remember that your vigilance, your attention, is largely governed by this particular structure, the amygdala. So all these together, pretty much we're talking about those things we discussed at first: reward-related learning, inhibition of your behavior, and decision-making. This is the really great stuff, right? This stuff, right? Aren't you guys so tuned in to pathways? So the input pathways coming from a major switching center of the brain. Every bit of sensory information goes into this switching center except smell and gets farmed out. So the thalamus is absolutely essential. The hippocampus, all about memory components. And the cortex, all about all of the processing for all this, right? That's going to feed into the basolateral amygdala. Remember, all sensory information is coming this way, but that sensory information from the thalamus has a short circuit. It has a quicker route, right? The first place we're going to talk about is the orbitofrontal cortex. Why? It's a hugely important area. Almost all your sensory information is collected here. And figure out, what do we do with it? How do we deal with it? Those fajitas coming, I can see them, the smoke rising, I can hear them sizzling, I'm starting to salivate. All of that coming together is coming in to that orbitofrontal cortex. So having a link to that is incredibly important. Where's that sucker at? Well, it's right there. Right there. Amygdala back in this region and our orbitofrontal cortex. Major part. The hippocampus. I already saw a picture where that is. Again, it's all about our memory of fear. And so recall, here's our amygdala, there's our hippocampus, and very intimately associated. Dorsal and ventral striata. Don't expect you to know everything about these parts, but it's important to start putting things into context and how many influences the amygdala has throughout the brain. avoidance behavior. We'll talk about that when we get into the ratonis, right? And there's the dorsal ventral striata in the brain. And finally, of course, the major pathway we're talking about is the pathway to the central amygdala, all about your autonomic responses to fear, making sure if you're giving a public speech that you feel just like a lion's about to attack you, right? Exactly the same processes going through as that a lion's about to whip your butt, right? Also, we're going to have outputs through the central amygdala via the bed nucleus of the stria terminalis. I love that, BNST. Ooh, this gives you goosebumps, right? All right, anyway, this drives your attention to stimuli and also has to do with signs of anxiety. Bed nucleus is right in that region right there in the brain. All right, where does the CEA go? Well, right, we're sending out the outputs from the basolateral into the central amygdala to the lateral hypothalamus. And if you know anything about the hypothalamus, it's responsible for homeostasis. What the heck is that? That's for making sure you remain alive, for one thing, but it also regulates your sex drive, your drinking behavior, your eating behavior, everything that's needed to keep you going and moving about the world, right? So very important outcomes that result from stimulation of the hypothalamus by the central amygdala. And here are the lateral nuclei of the hypothalamus right in that position. DMNX, oh God, I mean, these acronyms are just so powerful, right? Dorsomodal nucleus of the 10th nerve. What's the 10th nerve? Vagus, sweet, all right. The vagus nerve, right? It's all about that parasympathetic side, getting us to relax, getting us to our heart rate to go down a little. So we're going to be dealing with these conditions, right? Why do you see, if you remember in The Exorcist, right, Reagan comes down the stairs and pees all over the carpet. Why do you pee when there's this incredible intense fear? There you go. Now you know. You can say, I know now, it's the dorsal motor nucleus of 10, and that's what's happening. Also, the nucleus ambiguous over here. This is a slice through what's called the pons, the rostral pons. Okay, we're dealing with all kinds of different regions. Also in the pons is the parabrachial nuclei, and they're all about, you know how you can't really get that respiratory under control when you're very hyper and anxious. And so this is the brain stem coming up, and the parabrachial are right in that region right there. Love that stuff, right? Right? Oh, it's just so awesome. Oops, I want to go back. So then we've got the, I'll get it right one of these days. Hold on. All right, then we've got the ventral tegmental, the locus ceruleus, the tegmentum, the basal forebrain. These are all the major neurotransmitter outputs we're going to see here. In this one, ignore, this is about other things like diet and stuff like that and attention and stuff. But we have here, you can see the tegmentum. It's pretty much this whole region right here that includes the raphe, where all serotonin's made, the LC, where all norepinephrine is made for the brain, and the VTA, where all dopamine is made in the brain. We're leaving out one of the other major neurotransmitters, and guess what? The basal forebrain is the center for making all acetylcholine in the brain. So we've hit all big four here, except for GABA. That's another story. We'll talk about that some other presentation. Okay. All right. Pontine nuclei. They're in the pons somewhere. Okay. Startle reflex. Very important, right? Somebody comes up, crashes cymbals behind you like that, and everybody laughs. You can't help it. There's no way not to. I say that because it happened to me numerous times because I was a band goob. So you can't help it. You have a startle reflex. And they're basically right in this position. This is a slice through the pons. The central gray. Small little spot in the brain, but oh, it's massively important. Here we talk about freezing. So if you're, if you've seen those stupid horror movies, they're walking along and then all of a sudden they hear something, they'll stop and freeze. So this is part of that behavior. But more importantly, it has to do with rats getting shocked, and we'll talk more about that later. And so right there is the central gray, and there's this enormous set of axons and pathways called the reticular formation that pass through there. And so this area actually has an incredible effect on those. The trigeminal and facial motor nerve, right? What makes those facial expressions go crazy? right? And so here's the facial motor nerve, all those yellow branches you see there, right? You're going to make that kind of, maybe not exactly like that, but that kind of statement. And then the trigeminal nerve was in the other picture. And finally, the hypothalamus, that's where we get our corticosteroid activation, and you get that beautiful cascade of autonomic responses that I'm still experiencing, by the way, just to keep you up to date. I don't want you to feel like I'm calming down at all. And so it's like very near the thalamus. Okay? All right, unfortunately, that's it for the major pathways. Let's get on to some stuff that maybe is more interesting to some psychology people. I don't know. I thought it was interesting. Okay, so the more active the amygdala is when you are capturing an event, then the more profound and enhanced the storage of that is. Name something that's happened that you remember and you think you'll remember till the day you die. 9/11. Beautiful. For me, it was JFK dying. It's my first... I mean, I have other memories, but this is my first profound memory. Yes, I was alive in 1963. Okay? Fortunately, I'm still alive. But I remember the channel. I remember visualizing it on the TV, black and white, my mom's reaction, my dad's, Walter Cronkite. I remember that. He was crying, and I just visually remember that. My dad was a editor for the space program, so for me, the Challenger explosion, I don't know, for some of y'all, got a profound, I remember the exact instant I heard about it, and then, of course, as you pointed out, 9/11, I'm sure we all pretty much remember where we were there. And that's due, you can thank your amygdala. Right? So what happens then if we start to screw around with this sucker? All right, well, there's a genetic disorder called Williams syndrome, and this genetic disorder, it leads to these individuals being extremely trustful and gregarious. What's gregarious, right? What's that? Easygoing. Easygoing, very friendly, love to be around them. They're just a joy. And they also suffer, I don't want to imply that everything's hunky-dory, they do suffer from forms of mental retardation, learning difficulties, I should say, and also have very distinct facial appearances, as you might also observe with Downs, although they're completely unrelated. All right, so what can happen here is you will get no activation. You can show them the worst possible image. We could have that Charles Whitman stuff. They could be there live looking at it with these bodies with blood draped all over them. And they'd probably go jump on the body and, hey, what's up, and have a party with it. That's how trustful these are. So their amygdala are obviously not providing the right responses to them to be, wareful about what's happening around them. And so that's serious, right? If you don't have a proper perspective on your surrounding environment, that's an issue. That can lead to problems. Social phobics. I've gotten to be more like this as I get older and older, but social phobics, their amygdala results in any face that's being presented to them being a major issue, very fearful of it. So this is the alternate, right? So we had Williams where everybody's trusting, but here everybody's scary to you. Right? And then what about clinical depression? Well, in clinical depressed people, what do you think they might be most fearful of? Death? Ouch. What are depressed people normally like? They're very sad, withdrawn. What would make you feel worse if you're around another or a lot of other sad, withdrawn people? And what begins to happen in clinically depressed people, sadness is fear. It becomes equated. So these are all consequences when amygdala that we are naturally given. I shouldn't have probably used altered because that implies some kind of surgical alteration, but they have different amygdala and lead to these different conditions. All right, the good stuff, right? Animal experiments. It all began with Kluver and Busey. 1930s, right? They took a bunch of monkeys and whacked their temporal lobes. Basically just went in and cut them out to see what the result was. And of course we know the amygdala is in the temporal lobe, right? But unfortunately they also yanked out a lot of other fairly necessary structures. A few things in your temporal lobe you need. What happened is the monkeys become tame. If you've ever been around monkeys, I used to handle monkeys in one of my old jobs, they are not tame. There is no way you could ever ever account for them being tame. And also in the presence of fearful stimuli that normally scared the crap out of them, like rubber snakes, they have no reaction to it anymore. They lose it. Okay? And what happened is, yeah, these guys showed that, but later on now they have gone in and selectively removed or extracted the amygdala, and these same things result. Okay? So it turns out if we play with cats, right? Cats are fun to experiment on as well, just like monkeys. And they'll get very defensive and flighty, and you know, cats are normally like that. I'm not quite sure how they figured this out, but anyway. And also, I just want to dip this in there. We are animals, and I just want to kind of put that in there, that if we stimulate the amygdala, we'll get fear and anxiety in humans. We'll get more into that a little later. And of course, all the other little aspects we've already talked about in terms of autonomic evaluation. It's really hard to talk about amygdala manipulations because when they go in to, say, lesion it in an animal, the lesions have to be incredibly precise. You come up to the conundrum that, are you lesioning just pathways that are passing through? They have nothing to do with the amygdala. Are you lesioning those? Or are you truly taking care of the amygdala? And so there's a lot of confounds there to interpreting some of this data. And I never, ever want to give you the impression that everything's solved and this is the absolute here with amygdala. All right? So more animal findings. Look at that. So monkeys that had bilateral lesions had a lack of normal fear response. They didn't worry about a rubber snake. They showed incredible behavioral changes. Just like us, they like to be popular. Well, they weren't so popular now. They did things that really irritated the crap out of their partners. They, you know, monkeys like to pick lice off in little mugs and eat them and groom their partners and so forth. These guys would do it in a very obnoxious way, and they'd get the crap beat out of them. I mean, that's what happened. So, and they didn't react to that. You know, the monkey that was getting annoyed would go, oh, right, like monkeys do, and nothing would really happen, and then they'd get their butts kicked. Oral tendencies would increase. They'd start, you know, those kind of activities that monkeys like to engage in. One of those 4 F's, I think, that, or at least related to one of those 4 F's, right? They'd get punished then and just absolutely brutalized. Let's look at the ratonies. Pavlovian, right? You guys all know what Pavlovian is, right? We had the dogs, we'd ring a bell, feed them a little after, right? They'd start associating bell ringing with eating, and then eventually you could just ring the bell and laugh at them as they salivated, right? So it's the same kind of thing. Same kind of thing. Rats are exposed to a tone. It's called a conditioned stimulus. And at the same time, they're going to get a shock. I'm sorry, I shouldn't laugh. But at the same time, right, they're going to get a shock. And so they start associating a tone with a shock. And pretty soon you don't have to give a shock anymore. You just do the tone, and they do what's characteristic of them at this point. They freeze. Okay? And there's little guy freezing. Poor guy, right? He's getting shocked right now. He just had the tone, and he got whacked. All right. I know I feel so superior when I'm showing you a rat that's having that problem. Subsequent presentations of the tone then will elicit a reaction even in the absence of the foot shock. That's what Pavlovian's all about, right? And what's neat, though, is that if they lesion the amygdala, you get a reduction in that freezing. And what's even weirder, right, is if you lesion them before all of this experimentation, they don't ever associate the two together. They don't associate the sound with the shock. Wow, weird. This is really powerful for showing what the amygdala is doing. So it's obviously, as we start to sidle our way into the human world here, then we're going to look at its role in evaluating emotional stimuli and how we get those stimuli to predict bad things that are going to happen. Because that's what we want to do, right? That's what we're hoping to do. We're hoping to maintain a great deal of attention to something until we're sure we're safe from it, right? And we're okay. All right. Well, it turns out, probably at some point, hopefully you've heard about frontal lobotomies, right? And those were all the rage in the 50s. Oh, go get a frontal lobotomy. Come out, go to the spa, right? Go to have a frontal lobotomy. And in some individuals, they did actually do quite a bit of good. And so subsequent to this is a few years after frontal lobotomies were really getting going, they said, well, we've got these individuals, these young kids, that by the age they hit puberty, they're too violent to remain in home. And so they have to be removed and put in hospitalization. But they're too violent there as well. So the issue comes about, what do we do about that? How do we deal with it? And somebody came up with the idea, hey, instead of the whole frontal lobotomy there, let's try an amygdalotomy. And so they yanked those out, and they called this taming. Okay? All right, kind of a nice little euphemism for it. Thousands were made, and it is actually still conducted, although very much more rarely today. The problem here with interpreting any data from it is, as I mentioned, every doctor took out varying amounts of amygdala and lesioned it in a different way. But in general, about 75 to 80% success at provoking fear and at being more difficult to provoke fear and aggression. Hyperactivity, which was also noted quite often, was decreased. Emotional control was enhanced. And there are 2 patients, but in interest of time, I'm going to skip that. All right. Just to wake you up again. All right, so there's this fascinating patient, SM, and known by the 2 initials that are totally random, right? They just identify her that way. She shows up at an Iowa hospital with an epileptic seizure. What's the first thing they do? Throw in an MRI. Let's see what's up, right? She ain't got no amygdala. What the heck is up with that, right? What up? Right? Well, so she has a rare genetic disease called Urbach-Wiethe, and it doesn't even always end up like this where you lose your amygdala. But what happens is, for whatever reason, in that one area of the brain, it calcifies and the amygdala are destroyed. So she doesn't have them. So, oh boy, now it's an N of 1, right? And in these types of studies, you always have to keep that in the back of your mind. There's a lot we can glean from them, but we always have to be cautious about interpreting it too far. She's perfectly normal in terms of acquiring new intelligence and anything else you would expect a normal person to be able to do. She had no fear, though, in these situations. What the heck is that? It's a snake, right? So what was funny here is they had a bunch of grad students take her out and try to scare her, right? So this is a really heavily controlled experiment, right? So they took her to a pet store and had all these snakes in it, and she just is playing with the snakes, and then she sees some big old constrictors. She wants to run over to those, and they show her tarantulas and scorpions. She wants to pick up the scorpion, so she exhibits absolutely zero fear. You know, you always have to wonder, well, is she playing along here? But they were convinced by the end of the day that she didn't. Theirs is a big old haunted house. They took her there, and all the grad students said, yeah, we got the crap scared out of us. But she was laughing and wanting more and more. Then they showed her, right, a great job, right, as a grad student, having to take her out and do this. But they took her to a movie, 10 movies, 10 of the so-called most scary movies of all time. 7, have you seen that, right? Pretty wicked, pretty ugly. The Exorcist, of course, that you've seen a few times already. All right, so couldn't scare her. She had no problems. SM had damage to both amygdalae. She exhibit, though, an absolute insensitivity to facial expressions that showed fear. Right? She could recognize people, wasn't that, but it was the fact that she could not recognize fear, and in fact, she couldn't even mimic it. She couldn't imitate a fear response with her own face. So, so this demonstrates quite clearly that, well, again, N of 1, but that the human amygdala has to be responsive to facial emotions and expressions, but in the most clear sense is most related to fear. Okay. So what did we conclude about SM? She has no fear, no anger, she can't read it, she can't mimic it. How does that work in comparison to Williams syndrome? If all faces appear trustworthy and amicable, social risk increase, right? You're putting yourself out there hoping you're not going to get stomped down. Of course, that's not going to deter you anyway. Somebody yells at you and screams at you. Well, you don't know any better anyway, so you keep doing it anyway, right? So, But what's really critical is it increases your chance to be damaged in the vulnerability. All right, so this walnut, or this almond, has a bit more to it than we might imagine. What can we do to scare? What is possible to scare? Well, they began tinkering around with increasing CO2 levels. So put a mask up that has normal flow in it, normal oxygen amounts, and start to increase the CO2 content. The brain is much more, the medulla oblongata especially, is much more attuned to CO2 than it is to O2. O2 is really not that important. It's all about CO2. So what they imagined is that this is going to, God dang it, is this is going to initiate a starvation kind of feel for air, and you're going to get scared, right? Because you feel like you're not breathing right. You give it to normally anxious individuals, and they lose it. They get really scared, and they'll have panic attacks quite often. You give it to normal people, no effect. And I know normal and anxious, I know, but for ease of use, just understand when I say normal, it means totally different things than you might expect. All right, so what would you expect, right? She doesn't have amygdala. She shouldn't respond at all to this particular issue. She should be like those people that are normal and have no response to slightly increasing CO2 levels. But then you get these anxious people that do have it, but they have amygdala that are probably really firing like crazy when they start getting those CO2 levels going. But then she doesn't have them, but yet she has this response. She is very anxious, and she's just like those people. And what they did is they found 2 other test subjects. Wow, we got an N of 3 now. We're rocking, baby. And so what you see is this black hole right here, that's where the amygdala should be, and it's gone in all 3 patients. Right? They had another disorder that can lead to that. There's an encephalitis problem that can lead to destruction of the amygdala as well. Data, sweet! Love data, right? So we have the 3 patients, an N of 3. This is an N of 12. And in these 12, this comparison group that they picked out, you had panic attack rate of 25%. That means 3 people panicked, right? 9 didn't. So we separate those out, right? Here's now your panicky people that have amygdala and your ones that have no amygdala. And yet there's no significant difference between these 2, but there is significant difference between them, and that even with an N of 3, enough power is there, enough of a difference to claim significance. All right, let's get to those bad old males here. There's 2 basic areas of early onset, and I'm sure you guys could correct me on that, but early onset conduct disorders occur before 10, juvenile after 10, and impairing obviously occurs across several interactive settings. Right, so you're not going to function very well if you have conduct disorder. We always argue that maybe one of our sons did. He at least had oppositional order disorder, right? So, that's okay. I'm used to it. Trust me, it is absolutely no big deal. Early onset experience more lifetime conduct disorder symptoms. So think about that. If you're early onset before 10 and you have conduct disorder, then you're going to be worse off later in life than your corresponding adolescent onset individuals. Kind of makes sense. You've got a head start on things. You can really get going, figure out all kinds of new ways to get in trouble, right? Plus, they're going to show aggressive symptoms. So what'd they do? Well, they took these individuals and they did some fMRIs on them. And what happened is they both showed decreased volume in their bilateral amygdala. This is relative to some matching comparison subjects they had. So this seems to be a general characteristic of male adolescents with conduct disorder regardless of the age of onset. More data. Sweet! All right, so here we see, and you tell me if you see any difference in these pictures. I suspect the journal screwed up on the pictures, but this is basically normal. These are healthy individuals, and here you can see a dramatic reduction in the amygdala area. Again, I suspect there's an issue here because look at the data. Here is your early onset amygdala volume. Here is your adolescent onset amygdala volume. much more decrease between the three. These are significant compared to the control. All right, so what's the conclusion? Well, the adolescents had a larger reduction in amygdala. But that's a confound, right? What did we just say? It's worse for adolescent early onsets later on in life than it is the adolescent onset. But adolescent onsets have more reduced amygdalae. So everything is not as simple as it appears, right? Chicks, man. All right, we got the guys out of the way. What about females? Well, you know, when they have conduct disorder, they go out and get pregnant. They can also show signs of antisocial disorder, certainly continue health problems into adulthood. And as it turns out, they both have very similar cortisol levels. Remember, the amygdala is hooked into the hypothalamus that controls those levels. So there's some extensions going on here. We don't have fMRI data here, but we do have cortisol data that implicates the amygdala. All right. I want to hit this, and then I'm going to skip on back. This is the notion of the born criminal, introduced back in the 1820s when they started really getting kind of into some more detailed detective work and things, right? So this guy named Lombroso decides that, hey, you know, maybe you're born to be bad, right? You're born to be bad. And so maybe you're just predisposed to be a criminal. Well, this incredible study looked at these kids at age 3, and they evaluated what's called the electrodermal response, right? Associated with sweating and so forth, and how much something irritates the crap out of you. This is on the island of Mauritius. They looked at 1,795 kids, and they looked at them again 20 years later when they were 23. And they evaluated, did they have criminal convictions? So all of these 1,795 kids, how many of them had criminal convictions? We have a measure of how they responded when they were 3. Did they show any indication, perhaps? I'm not saying that it's an absolute link, but perhaps if you show these signs even that early on, maybe it's something like Minority Report, right? We can identify criminal. No, it's not going to ever be like that. But what they did is they used a match design. They did all kinds of tests and so forth to make sure the matches were correct. And what they did is at 3, they gave them this particular test. This CS, the conditioned stimulus, right, was a 1,000 hertz tone. You notice those figures there. And look at the one where it's negative. So what that means is after this one, you're going to get something bad. After this one, you're not. And the only way you're going to tell a difference is the difference in the frequency of the sound. What's the bad thing? It's this really annoying, irritating. I should have had a little audio of it. But it's these metal objects in this can, and they're just whacking it back and forth, right? Really irritating, really annoying. And it's a very loud sound. 90 dB is incredibly loud. What happened? Well, in those subjects, so back here, right? So at the age of 3, we evaluated these particular individuals. Those people that we evaluated at 3 and that later had criminal activity, right? We evaluated again, or we evaluated and we went back and looked at their data at age 3, and what we saw is if they were later going to become criminals, they had no response to this jangling, intense sound that was happening. But if you were a non-criminal, you had an intense reaction to it, and the electrodermal response was significantly higher. So basically what we're saying is, if you're going to be a criminal, you pretty much don't care. You're not going to respond to stimuli in the same way as other individuals. So poor fear conditioning at 3. And I underline this word because I don't want you to think, again, there's a direct link. Predisposes to crime at 23. This implicates the amygdala and the orbitofrontal cortex. All right? And these findings are all consistent. All right, there's this youth thing. I don't want to go through that. It's just more data. Let's go ahead and skip forward. Psychopaths, right? Sweet, right? So psychopaths lack empathy, guilt. They could care less about anybody. They think they're the greatest thing since sliced bread, right? Very poor behavioral controls. They really have an incredibly difficult time processing this fear and sadness. So what they did is they looked at 27 sufferers, and though this isn't strictly psychopathy, the people that did the study considered it that. They had matched it to 32 non-psychopaths, and what they found in the fMRIs that you really can't see too well up there is that the psychopaths exhibited quite a few malformations in the amygdala. 18% reduction. That's huge. That's a huge part. And so then they looked, these were just general ones. They pulled off roles from temporary employment agencies. I'm not sure what that means about temporary employment agencies. But down here, then, they looked and went into prisons and looked at criminal psychopaths. And what they found is they show less affect-related activity, in other words, emotional responses, than did non-criminal controls. All right? So they show bilateral amygdala reductions, and we see the data there that you can barely see, but this is the psychopaths, the criminal psychopaths, versus the controls, significant reductions in both amygdalae. Finally, we get to the happy thoughts, right? Lots of doom and gloom, psychopaths, whatever, but they do seem to exhibit laterality, and what that means is the right side is a little different than the left side in terms of how it processes things. The right amygdala seems to be mostly associated with fear and panic, while the left has a larger role in pleasure and happiness. Data, sweet. This is a scores of IZARD. I'm sure you guys know a lot more about that, but it's, of course, a test. And what they would do is, these epilepsy patients, they're in surgery anyway, right? So, hey, let's zap their amygdala and see what happens and see how they feel, right? So they looked at, so all the white bars are before, and you can see lots of this stuff, this bad stuff, getting boosted here in the right amygdala. They never had a right amygdala stimulation report a pleasant state. So in the left amygdala, though, they had a split in patients, and it depended where the stimulation occurred at in the amygdala. If it occurred in a certain part of it, really not much difference than the right amygdala. But in another area, notice the happiness was way up there, the surprise, and if we look at an overall summary of the data, you see zero effect in the right amygdala on joy, but a massive increase in the left, and then happiness, zero in the right, massive in the left. So there are also many positive aspects here. Conclusions. It's always on. It's always ready. 24 hours a day, the amygdala does not sleep. It's ready to go. But it's under control by the prefrontal cortex. Think about going to a zoo. You should be really scared of those wild animals there, but you're not. That's because your PFC, your prefrontal cortex, is taking care of things, keeping that amygdala in line, not allowing it to get out. Numerous interactions with the frontal lobe. This is going to be key to figuring out what the heck to do with the PTSD that's happening. PTSD appears to be more hypervigilance, not hyperfear. The amygdala is on too much. It's stimulated way too overly much. And it's cute and cuddly, right? All right, so, okay, she won't ever stop till I turn that off. All right. Made it just in time. If you do have any questions, I'll certainly hang around a bit. But I do appreciate your interest and presence. Thank you.